One of the most important fundamentals to understand in databases are the back end of tables and indexes and how are they stored on disk. And you're going to see me mention these fundamental, concepts and pieces. And I want you to understand them before jumping deep into the course. So this lecture will discuss these different concepts, how tables are and indexes are stored in disk, and how they are queried, and what's the cost that is associated with knowing these concepts. Let's jump into it. So here's all the storage concepts, and not really just storage, it's just the operations that are performed on the storage itself. So we're going to discuss what is a table. From a logical point of view, we're going to discuss the row ID concept, the unique identifier of the row. We're going to discuss what is a page. We're going to discuss what's an IO, a heap, index data structure, B trees, and finally, we're going to give you an example of how a query performs on the heap versus an index. Let's jump into it. So we have here a beautiful table with a bunch of columns, right? And so these are the actual fields, the columns, and this is a row. Obviously, you might say that I work with databases that don't have rows, they have documents. It's the same concept. Once you take that idea of row, you can convert it back into, at the end of the day, it's all bits, right, and bytes, and the storage model just understands that, and that's where I want you to understand this row, this is a column. So what is the concept of a row ID here? Usually databases don't work with the fields that you provide them. Some do, right? But most databases create their own system maintained row, right? And this is the row ID effectively. And this is a position in the row itself, telling you that uniquely identified this particular row ID, right? In Postgres, this is also called tuple ID effectively, right? So this is another important concept to understand, right? Nothing so special. In MySQL, for example, the primary key becomes that pseudo row ID effectively, right? But in Postgres and some other databases as well, a new row ID is created on your column, and that is how it is referenced effectively. So what is a page really? So if we really thought about this table, right, as we're looking at this logical table, a bunch of columns and rows, what depends really on the storage model, whether it's a row store and a column store. I really want you to watch that other lecture where I talked about row versus column store. How are they physically stored in disk? Really matter. Rows are stored on these logical pages, and a page is really nothing but a fixed size memory location, which translates to disk location as well, of a bunch of bytes. That's it. It's a fixed size. Usually it's fixed size, right? And then you can put the row in the page. So technically a page can fit many rows. Now it depends how many rows. It all depends on the size of the row, right? And the size of the columns and the size of the data types of these columns. So the database really doesn't read just a single row. It's like, oh, go read me row number 1000. No, it's not like RAM. RAM is byte address, where you say, hey, go give me that particular byte location and just go read it. That's a random access memory, right? RAM. No, disk, on the other hand, actually just reads a page, right? And you tell me, oh, go make an IO and fetch me this much data, right? And when you do an IO, this input output, you get a page or more than one page. It really depends on the disk partition. How did you partition your format? You format your hard drive or your SSD. And it depends on so many other factors like the operating system as well. But when you actually read, you get so much stuff. You get one page or more. It really depends. But the beauty of this is one page can have many rows, right? Each page has a fixed size. Like in Postgres, the default size is 8 kilobyte. In MySQL, I believe it's 16 kilobyte. And you can configure those. So if I for example, say each page holds 3 rows, right? In this particular example, that means for 1001 rows, you divide it by 3, you get around 333 pages, right? And these pages are stored on disk, right? And when you look at them in the disk, it's just a bunch of ones and zeros, right? But they physically have a start and an end, which you define as a database. So this is how you look, and this is very critical to understand. It is not just theoretical stuff. This is what makes and breaks a database. This is what makes a query slow or fast. Understanding how many pages are you pulling, how many IOs are you making, because that's what actually a page is. What is an IO? An IO is an operation that reads request to disk. We try to minimize this as much as possible. This is the currency of a database. The less IOs you make, the faster your queries. That's what we need to make. So what does that mean? An IO can fetch one page or more depending on the disk partitions. I talk about that. An IO cannot read a single row. It's just a page with many rows in them. Right? And when you do that, you get many rows for free. You don't get to say, oh, I want this page, but I don't want this stuff. Sorry, you don't get to do that. Oh, I want this page, but I don't want the date of birth. I want this page, but I don't want the names. No, you don't get to do that. That's why select star is very expensive. That's why select a name is very expensive as well, right? Because if you do select name from table, guess what? You're already going to the table, you're doing the page. If it's a row store, you're getting everything, right? And we're going to talk more about that in the course. Then the database has to filter out what you don't want and throw it away. The cost of deserializing the bytes back to the in-memory structure for the database to process is expensive, right? So you want to minimize these IOs. They're very expensive. Same IOs in operating system. Some IOs in the operating system goes to the operating system cache. This is specifically true for in case of Postgres. Postgres rely heavily on the operating system cache. So an IO doesn't really mean going to disk. So it could go to a cache that the operating system defines. So you're going to hear me as well talk about this a lot in the course. Heap. What is a heap? A heap is exactly what we talked about here. A heap is a collection of pages that represent points to your data table. It has everything about the table itself. So everything in the table is in the heap. We call it the heap because it's a special data structure that has pretty much all the data, everything, right? And that makes it expensive to query because it has a lot of data, right? So this is where the actual data is stored and everything. Traversing the heap is expensive as we need to read so many data to find what exactly we want, right? Because usually when you read stuff from the heap, when you try to find something, you're looking for a few things, but the heap gives you everything, and that's costly, right? This is why we need indexes that help tell us exactly what part of the heap we need to read. We don't need to read every single page in the heap. I want to know what page exactly to jump to read just that page. You can do that in the desk. You say, hey, go read me page 3333 and above. You can do that. But you can't say, oh, go read me row 7. Row. If you say go read me row 7, you gotta get page 2 and maybe page 3 and anything that's next to it effectively. Let's talk about the indexes. An index is nothing but another data structure. No magic. It's just a bunch of other data structure that helps you pinpoint exactly where to go into the heap so you can fetch the information in an efficient manner. So an index is another data structure separate from the heap and has pointers to the heap, right? And these pointers is just literally numbers that point to the row ID that we talked about. And the row ID has more metadata about the page in the heap that we need to pull. It has part of the data and used to quickly search for something. You can index one or more column in the index effectively to create this data structure. And this data structure uses something called B trees, which I have an entire section talking about effectively. Good. So yeah, because you cannot index everything, right? You index exactly what the things you need to search for. Once you find a value of the in the index, you go to the heap to fetch more information where everything is there, right? That's what the point of the heap. Index tells you exactly which page to fetch in the heap instead of taking the hit to scan every page in the heap. The index is also stored as pages and cost IO to pull the entries of the index, because guess what? When you think about the index, it's not something magic, right? It's a bunch of, guess what? A bunch of another data structure, usually B tree, and that B tree, you need to read it in order to understand, to parse this content, right? And this lives on disk, because when you spin up the database, you need to read the index from disk and pull it in memory. Some indexes fit in memory, others don't. If you have an index that is so large, it doesn't have to fit in memory. That makes in searching the index to know what to pull right from the heap can be expensive, and this is what I want you to kind of understand and pinpoint here. The smaller index, the more can fit in the memory. Popular data structures for indexes is B-tree, it can be LSM data structure, Brin indexes, you know, many other type of indexes. Learn more on the B-tree section. All right, so this is how it looks like on disk. This is a very simplified view, guys. So take it with a grain of salt. This is not exactly how it looks like, but it helps understand. So this is the heap. So we have a page. We have row ID 1. This is the the employee ID, the name, the date of birth, the salary, and then immediately the next employee row starts, right? It's in the same page. Row ID 2, 20, Adam, 97, and then Ali, 5, 2, and then this ends page 1. I simplified it. It's exactly identical to this, but I just said row 5, 4, 5, 6, because the 3 rows in a page. Remember that was our condition here in this particular example. 7, 8, 9 in page 2. So 10, 11, 12 in page 3, and page 33 will have 3 rows, the 1000, 999, and 998. So this is the heap, right? But in the index, if you think about the index, it, like, let's say I indexed on employee ID, which is this 10, right? So you're going to see only the employee ID here. So 10, 20, 30, 40, 50, 60, 70, 80, 90, right? And then up until 10,000, which is the last employee 10,000. Okay, I have all the employees here, but that's just their IDs. And look, what do we have here? This is the point that we talked about. It says, okay, employee ID 10 lives in row ID 1, has a row ID 1, and lives in page 0, right? Employee ID 20 lives on page 0 and row ID 2. Employee number 110 lives on page 3, and he has a row ID 11, and so on, right? This way, if you search the index, and searching the index is just another IO, as we talked about it. Now, it's not sequential as I'm showing it here. It's more a little bit complicated than that. It's a B tree structure, so it's an actual tree where you go to the left if it's less, and go to the right if it's more. I'm gonna talk about that in details, but take this with a grain of salt as an example. So let's say I want to search for employee, I don't know, 40, right? So 40, I pull this page, so I did an IO on the index. Oh, I found for employee 40, but hey, wait a second. I don't want employee 40, I want their name, for example, or their salary. Oh, you need to go to the heap. What do? How do I know which page to go to the heap? Well, employee 40 have his row ID 4, and it's page 1. So immediately you do another IO on the heap, says, oh, give me page 4, page 1, and give me row ID 4. So you go to the row ID 4, you discard 5 and 6, because guess what? You did an IO, you got 5 and 6. You cannot escape that. Well, that IO gave you all the stuff, right? And you give you 5 and 6 and their birthday. You got the salary of 6. You get the date of birth of 6. You get their name of 6. You get all the stuff, but you only pick exactly what you want from 4, effectively, right? And the database does all this magic behind the scene. So think about just that. So this is much more efficient, right? If this query is fast, and if this query is fast. If you're asking for more, it's gonna do more jumps here, right? So let's take an example. So let's say I don't have an index. I only have a heap. And I want to do a select star from employee table where employee ID equals 10,000. Well, in this case, guess what? Employee ID doesn't have an index, right? So what do? Well, I don't have a choice. I have to go query page 0. How many rows do we have? We have row ID 1, which is 10, 20, and 30. Employee ID 10, employee ID 20, employee ID 30. Oh, none. Discard the page. Go to the next page. Page 1. 4, 5, 6. Nope. 7, 8, 9. Nope. Up until you doing fetching all these pages. This is so expensive. Some databases does parallel threading, multiprocessing to kind of walk this structure by using multiple threads from down and bottom, from down to top, and in parallel to scan. But in general, it is expensive because the last page happened to be the one that have employee 10,000. So we did a lot of queries to fetch that. So that's without an index. Let's do it with an index. So now the query with the index, in this case, we're going to query employee ID 10,000. And here's where the B-tree query actually takes place. And it goes through a tree until we find exactly the page that we need to look at. And the moment we find the page in the index, oh, this is page N, we go to the page and then we find that exactly employee 10,000, right? And this is row ID 1000 and it's page 333. So once I got that tuple, that information, now I go to the heap and they say, okay, go page 333 and pull row 10,000 and return it to the user. So immediately we know which page to pull, and immediately we get all the information. And then finally, I have some notes here that I just added so we can discuss and in this lecture. Sometimes the heap table can be organized around the single index. Right, so we did show that index is a separate data structure from the heap, but sometimes the heap, as you saw in this lecture, is not really organized. It's not ordered, right? But the heap can be ordered around the index, and in that case, it's called a cluster index. And I talk about it in this lecture as well, in this course, sorry. And it's also called the Oracle terminology is called IOT, or it's called Index Organized Table, IOT, right? So I just fixed it. So yeah, so this is called an IOT, right? An Index Organized Table, where you have the table organized around a single index effectively, and this is called a cluster index, right? And it has a pros and cons. I can't go into this in this lecture, but I'm gonna talk about it in other lectures as well. Primary key is usually what is called a primary as a cluster index, unless otherwise specified. And whenever you hear the term primary key, that means it's a cluster index usually, unless it's Postgres. Postgres primary keys is just a secondary key, right? So MySQL and InnoDB always have a primary key. It's always have a clustered index. So if you define a primary key, the table will be organized around that index. So be very careful about what data type you pick. I talked about this a lot. The idea of having, for example, a UUID, which is truly random, in a cluster index just kills the performance when it comes to writing. Because now, if you insert a UUID, a random thing, now the heap have to be organized around the index, which is your UUID, which is random. So you're gonna be hitting multiple pages because every UUID is random. So it will live in another completely random page, and this scatter shot is very, very expensive, and I talk about it in many things. And ask questions, guys, if you want me to explore more of these. Postgres have only secondary indexes, and all indexes point directly to the row ID which lives in the heap. So this is different than the primary key, right? So in case of, if you have a primary key where you have a clustered index, the primary key itself is a kind of almost like a user defined field, right? But any other index will point to the primary key here. But in Postgres, everything is a secondary index. We have this row ID, which is a system maintained field, that every index point to the row ID, which means if you edit anything in Postgres, all the indexes get updated. That's a cost that you have to to understand, right? It just all makes sense once you understand these low-level things. That's why I wanted to make this lecture. And finally, let's make a summary. We talked about what a table is. We talked about the row ID, which is really, it's a system-maintained field that some databases add, some don't, right? Some rely on an existing primary key that the user defined. We talked about page. A page has it's just a fixed size, right? Some pages are dynamic, but let's talk about fixed size. It's just easier to deal with fixed size pages. 8K in Postgres, 16K in MySQL, and you can put rows in them. You can put columns on them, right? You can organize the page around columns, which is something I'm going to talk about in the next lecture, right? IO gives you one or more pages. You don't get a row or a byte in an IO, you get a lot of stuff. So the key here is if you do an IO and you get everything you want in a single IO, that's the beauty. That's the efficient IO. You want your IO to be efficient. Heap data structures, right? We talked about that. Index data structure, B-trees, and we gave you some examples. All right, guys, I'm going to see you in the next one. Thank you so much. Row versus column-oriented database storages are two styles by which databases use to store their tables on disk. Each have pros and cons. Nothing is perfect. There are use cases for column-oriented. There are use cases for row-oriented databases. In this video, I want to discuss what is a row-oriented database, or also called row store database, because that's the store type. How is it stored on disk, right? I'm going to also describe the column-oriented database, or also known as column store, or another fancy name is columnar database, because yeah, why not? Just let's confuse everybody by inventing new names. So it's all the same thing. It's just how things are stored on disk. We're going to talk about the difference, these two. And then finally, we're going to discuss pros and cons of both. How about we jump into it, guys? All right, guys. So let's say we have a beautiful table like this. Okay. It's an employees table. It doesn't only have 8 rows. It has thousands of rows, right? But for simplicity, we only have these. These are the columns. Straightforward. And the first, I want you to pay attention to this. This is the row ID. This is how databases, it's a unique identifier that identifies the row. It's different than the primary key or this ID. It's just something that has, most of the time, most databases have this internal mechanism to identify this row. Okay, and I want you to pay attention to this. So if I'm gonna submit a bunch of queries on this table, I want to do this without any indexes, because indexes will just complicate the manner and by way we think about column versus row oriented. I want to take them out of the equation and think about them just, we don't have any indexes, we're just scanning the table to answer these following questions. So these are the following queries that I'm going to execute on a row database, and then I'm going to execute the same exact queries on column database and see which one does best for each style of how we're going to store these tables, right? The same table, we're going to store it on row, the same table, we're going to store it on column storage, and then we're going to look how these queries perform. So select first name from employees where social security number equals 666, the devil, and then we're going to select star from employee where ID equal 1, very simple, okay? And the final is the select sum. We're just gonna sum all the salaries of the employees for some reason. Yeah. So the first one, row-oriented databases, guys. So for row-oriented databases, tables are stored as rows on disk. And this might sound a little bit confusing when you first read it. I was like, of course. So saying, how else are you going to store stuff in the day? You're going to store row by row, right? So if you think of the disk as a blob, huge blob store of just things that contain just bunch of bits and bytes, then the rows are just contiguous, one after the other. So the ID followed by the first name, followed by the second name, then last name, then followed by the social security number, and then comma, and then the second row starts, right? And then so on. Each row obviously has a different size, It could be variable size because I don't know. So like my name is John Smith and someone else named Hussein Muhammad Nasser, right? So that's a longer name, so it's gonna occupy more storage on disk, obviously. And thus the rows can vary. But for simplicity, let's think about their fixed size rows. All right. When I want to read a particular row, I do an operation on disk called IO read. When I read that stuff, the controller, whether this is an SSD drive or a hard disk, reads in blocks. It doesn't read like bit by bit. Bit 0, 1, 0, 1. It doesn't read like that. It reads as blocks. So let's shove 512 bytes at a time. And when you, or I don't know, 1024 bytes at a time. It depends on the block size. This is something called block size. And once you read that, you're going to get not only one row, you could get 1, 2, 3, 4, 5 rows in a given block. So you get, the act of doing one IO can give you 5 rows. And just not all these 5 rows and all their columns, all their values. So whether you want them or not, you're going to get everything. You're going to get all the columns. So think about that. So technically, you need more IOs to find the row you're looking for. So imagine you're doing a table sequential scan on the entire table. So if you're looking for employee with social security number 666, you're going to have to do a block IO. You got, 7 rows, then search these rows one by one. You're only interested in the social security number, so you're gonna only pick that field. Unfortunately, you got all the fields. I'm not saying that's bad, could be good, depends what you're doing, but that's what you have to work with. So you have to do a lot of IOs to actually get to the row that you're looking for, because you spent a lot of wasteful reads pulling columns that you didn't need, and you don't have a choice. Right, so that's just one thing you have to think about with row-oriented. Does that mean they're bad? No, they are beautiful. They are elegantly designed because they are so simple. They are just rows, and you can easily think about them. You can easily implement them compared to what we're gonna come up next. So let's dive deep into this. So we're gonna take our table and then we're gonna convert it into a row based on disk. How will this look like? Let's take a look. This is how it's going to look like. So imagine this gray box as a block, right? And for simplicity, I put 2 rows in the same block. Could be 3, could be 4, could be 5. Who knows, right? It depends on the block size. But think about this as a given block, each gray box takes 1 IO jump to the controller to pull that block. So once you ask for this block, you got everything, son. You got everything, right? So now this is how it's stored. Basically, the row, comma, it's not really comma, it's just literally consequent, right, values, but I just added comma for you guys to understand. The ID, first name, second, last name, SSN, or the salary, birth date, I guess, when this John, the occupation, and so on. And so you can see that. And this, I added this so it can indicate the second row. It doesn't really exist. It's just an identifier, like to allow us that, oh, this is actually a second row just started and then a row just ended. And you can see that these are the 2 rows, 2 rows, 2 rows. So let's execute our first query against a row-oriented database. I'm looking for the first name for employee where their social security number is 666. The devil. All right. So let's pull it. What do? We ask, hey, because I don't know. I have to start from the top, right? Because I don't know where employee 666 is. It's not like this number, this field has any relation to the row itself. It's just a random value, right? So I have to pull the first block of the table. Does 666 exist in this? Nope. This is 222 and this guy is 111. That's the social security number. So let's pull the second block, right? Nope, it doesn't exist. This is 444333, right? And yeah, it might look sorted, but it doesn't have to be sorted, guys, right? I'm walking through that query with you. right? Again, no indexes, nothing. Now I'm gonna pull this next block. So I did 3 reads, and then I happen to find that 666. So I found what I'm looking for. Now I want the first name. Guess what? I don't need to do any extra read. Why? Because the first name is right there in the memory now. Because that once I pull this block, it's in memory, it's in the RAM. And when I ask for it, I don't have to go back to the disk because, yeah, guess what? I just pulled it, I found it, now I just, this is the first name. And I know because of the position. This position number 2 is the first name. So, boop, pull it. So, once I find something, asking for extra columns are really cheap because we already got them, right? Again, guys, you have to think about this. Whatever I'm going to explain to you, there is no bad or good. It depends on your use case, depends on your queries, it depends on your where clauses. And based on that, you pick row versus column based. We're gonna come to that. So that's the first query. Let's do another query. Okay, I guess it's executed immediately. All right, so we're gonna do select star from employee where ID equal 1, right? And since it's ID equal 1, if this is a sequence, the database can do tricks where it can link this sequence with the row ID. And it says, okay, ID1 is on row 1001, so I know actually where to jump and pull this row, this block, right? It doesn't have to read other things, but it happened to be that the first block is what we're looking for. So, we're lucky, I guess. But even if we don't have this trick where we link the ID to the row ID, we still have to go through each block, and once we find the block we want, guess what? Now I want all the columns. Can I do this? Absolutely. That is so cheap because all the columns are already in memory, assuming they are not vertically partitioned into another location, right? Vertical partitioning, I talked about that many times in my channels and my courses. So vertical partitioning where we take a column and put it somewhere else, right? This is not the case. Well, everything is in one beautiful block. So I pulled that block, I asked for the ID, I found the ID, and now the user is asking for every field. I always tell people that, hey, select star is bad, guys, stay away from it. But it really depends what you're trying to do. If you have indexes, try to do less of that select star. Select star, we're going to learn that it's the worst thing you can do in a column-oriented database. Select star. In row, you can live without it, I guess. Still, just be aware of that. So that's cheap. That's relatively cheap because I'm gonna pull all the rows and if they're everything in memory, beautiful. Assume it fits in memory. So could it only be one block? Not necessarily, because a row can span multiple blocks if it's too huge. Let's say that we have some blob here field, and then it's a bad idea to store blobs in line anyway, but let's assume you do. But that means this row can span 7 blocks, for example. So you need to read all the block. Not necessarily. The database are smart. It's going to read the first block, find the ID, and only the rows, the columns you ask for is going to ask for the rest of the block to fetch stuff. Databases have been doing this for years. They know what they're doing. But I want to explain how it's doing this stuff. Awesome. So let's do the same thing, but an aggregate. This is called an aggregate function, which is an aggregate is just grouping by something, right? So you work on one or few columns, mainly one or less. How do you work with less than a column? That's just idiot. I'm an idiot. Okay, so you work with few columns, all right? Let's say 1 in this example. Okay, so select sum salary from employees. Just sum every salary. Let's do this. So we pick the first block. Well, tough luck. I only wanted the salary. Tough luck. I got everything. Again, no indexes here. With indexes, this could be extremely fast, but I'm just telling you what the database does without indexes. So you pull this. Oh, pick the salary. It's 1001 and 1002. So we summed those two. Now let's pull the next block so we get the more rows. Okay, 1,103, 103K, 104K, sum them. And then pull. 105, 106. Sum them. So, guys, every block we pull, we're pulling row IDs, we're pulling first names, we're pulling last names, we're pulling SSN, we're pulling salary, we're pulling that, which we never use, right? So imagine if I only asked for the salaries, and if they were grouped nicely, that would be awesome, wouldn't it? But now, unfortunately, we're asking salary, but we're pulling all the rows. So that's a lot of I/O. So again, this is not just one read. It can appear in this screen here as a one read. If the row is long, you can read 7 blocks. So that's 7 I/Os, right? I mean, yeah, the databases can do a trick where they send one request asynchronously, read multiple blocks, but regardless, you're hitting the disk, which every time you hit the disk is a duck dies, essentially, right? So try to save ducks as much as possible. Save the ducks, guys. Save the ducks. So yeah, reading, and we're summing all of that stuff. That's not so bad, I guess. Yeah, but you read unnecessary information. That means you almost read the entire table, but you used very small portion of it. That's extremely inefficient. So raw databases doesn't do well this kind of queries, if you think about it. It doesn't mean it's slow. Really depends what you mean by slow. I mean, you've run these kind of queries. The databases do all kind of tricks to be fast, but if you think about the logic, and I'm not saying this is how databases absolutely work. They have all sorts of trick. Again, multi-threading, they send multiple threads. Postgres send multiple threads to read asynchronously. So they do all sorts of tricks to do fast. But let's discuss how column-oriented databases work. So with column-oriented databases, if you think about it, tables are stored as columns first in disk. So think about the first name column, the ID column, the last name column. So what they do is they take the first name and they take all possible values, John, Melissa, Rick, Paul, Hussein, everybody, and pull all of these into and save them in disk as consequent values. And then once that table is done and the last value of the first name is done, they start with the second one, right? Last name, and then so on. So you might say, oh, why are we doing this? And we're gonna come to that. So a single block I/O read to the table fetches multiple columns with all matching rows, right? So it fetches a column. It could be fetched one column or multiple, depends, right? It depends. Like if you have a small table, you can fetch multiple one. If you ask the database to say, hey, give me this, you're gonna get a lot of rows. That's the trick here. So a single column with a lot of rows. Less IOs are required to get more values of a given column, right? Because if you want to get, as we said, the first 100 salaries, that is extremely efficient in column-oriented database, because hey, just go to the place where we know we stored the salary column and just walk through there, because you're gonna see the values just consequent. We're gonna go in the example, and they are great on online analytic processes, as we're gonna see in the coming slides. All right, so let's take the same exact table and start as columns. Here's how it looks like. Again, the row ID is very critical here. The ID field is this. This is the first name, second, last name. I keep saying second name. Social security number. This is salary, the date of birth, the title, I think, and this is the join date. Look at this. So look at this. I want the ID 1 and this. Which row is this? 1001. ID 2. Which row? 3. 1003. Why? We're gonna see. Look at this. The row ID is duplicated in every column. So just like that, what is the first thing that comes to your mind? Oh, editing is gonna be painful. Because if you delete row 1004, you have to poof, 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 poof. You have to go and mark all these stupid columns, right? Or these blocks. Remember, these are blocks, right? So, and for fun, I split some of them and multiple blocks. doesn't mean they are like, I know this is an integer, for example, or string. I just split them for telling you that, okay, we couldn't store all 4 rows here in one block, so we had to split it in another block, right? So I can show you different kind of examples. Again, take it with a grain of salt. I just want to explain these things to you. So this is 1 block, 2 blocks, 2 blocks, 2 blocks, 1 block, 1 block, 1 block, 1 block. Okay, got it? Capish? So this is how it works. So they just store all this stuff in columns. So all the ID fields, the entire table is here, right? All the possible values. So this is not just one block. It could be hundreds of thousands of blocks if you have a lot of rows. Remember, everything needs to be updated. If you add a new row, you have to update it in all of these logical structures. So, that being said, now we know how this works. Let's put it to the test. Select first name from employee where social security number is 666. So now, the database will say, wait a second, you're looking for social security number. I don't need to look at any of other logical structures except for the social security, which is this puppy. This is the social security data desk, right? This is how we store. I know this is the location. So in disk, I know where to point my needle and read this stuff. So to search for social security number, I only need to pull this, right? So now I start reading block by block. I read first block and I got a lot of beautiful values. I got 555, 444, 333, 222, 111. We did not get 666. So, okay, no problem. Let's pull the second block. This is almost like the row base, but now at the column level. Does that make sense? So now we got it. Ooh, we found it. But now I need the first name. What? First name is not here, son. You only got the 66. Now you found that this is actually 1006. That's almost like how indexing works if you think about it. This is how Postgres stores indexes. It's actually, if you think about this as an index, it's almost very similar, right? It just points to the row. Now, 1006. Row 1006, I know this value. I know the row I'm looking for. This is very critical. And I'm asked for the first name. Where's the first name? The first name is right here. This is the first name. So I'm not going to read these blah. I'm only going to jump right here, right? So obviously we found this row, as we said, and then we're going to jump right, not the first block. I'm going to jump to this block. You might say, Hussein, how did you know that it's in this block and you didn't pull this block? Because I know the row number. And the database does all sorts of trick to so, okay, this block has only rows from 1001 to 1004, right? So I'm going to jump to block number 703 because it exactly locate the row I want, right? Because they have all this metadata, mumbo jumbo, right? Again, that's back to our question. The 1006 link with the block is all there. They know. And they pull it and they find it. So we had to do one jump, one block read, second block read, jumped back to another block read, and then we got it. So 3. Not so bad, I guess. Let's do select star from employee where ID equal, and let's see how our beautiful column index column storage do. All right. So ID equal 1. Again, I don't have any knowledge with this, so I'm gonna start ID. Where's ID? This is the ID. So I need only to read these structures, right? Let's pull it. Found 1001. It's 1001. So now I have knowledge of the row. I know which block to read, but the user asked me for everything. Okay, let's jump on. Okay, we found that. Let's jump on to the first name. We know which block to read, so this one. Boop. That's one read. Let's jump on another IO. Last name, because they want the last name. They want everything. Read. Oh, found it because I know. I don't need to read this because I only know which block exactly in each column to read to find my value. All right. SSN. Find. Read. Salary. Read. Birthday. read. Engineer. Oh, I have a bug here. I should have. I didn't stretch it enough. Engineer, read. And join date, read. What have we done, guys? This is the worst query. There is so much thrashing happening on disk that this is the worst thing you can do. Column databases just tanks when you do this, especially if you have a lot of columns and you're asking for everything. And if especially if you have like a lot of and queries or queries here where you had to jump to find the multiple rows, ooh, that will, dude, do that. Dude and do that. I'm talking to both of you. Dude, do that. Do not do this. Select star. Whether row storage, column storage, do not do select star. This is, do you know how many ducks die when you do this kind of queries, guys? You go to the database, you read all these things. Ducks, every IO kills a duck, right? Save the ducks, please, guys. All right, let's do this. Select some salary from employees. Now that we saw how horrible column-oriented databases can be, let's see how great they are. I want to sum all the salaries. Yes, sir. Where's the salary field? There it is. One read. Done. Done. Well, if you live in multiple blocks, you're gonna read the multiple blocks, but done. That's it. That's it. And if you have caching and stuff like that, woo. And by the way, I didn't mention something. If multiple people have the same salary, column-oriented databases do something called compression and aggregate. They actually, if let's say if 3 people have 100,000 salary calories. Okay, all of them have a lot of calories, right? So they have a lot of salaries, and then you can just have one entry, 100,000 with a comma base, right? So 1003, 1004, 1005, all of them have the same one. So this is even more compact. So this will give me a lot of bang for my buck by just doing one block. Again, sometimes if there's like a duplication, ooh, this is the best thing for column-oriented database. They just shove it in the same row because, hey, okay, they're going to do it as an array. We talked about that a little bit in my Postgres 13. Postgres 13, they just started doing this. Index deduplication, I believe they called it. B3 deduplication, Postgres version 13. They start shoving more duplicated values in a single leaf node so they can compress on. So yeah, pros and cons. Is this thing perfect? Nope, nothing perfect. It depends on your use case, guys. If you ask me, I still prefer row-based, to be honest, just simplicity of writes and reads. But there are some cases where you need column-based oriented. To summarize, right? Write and reads, you want a simple structure. And we saw how complex column stores are, right? They're very complex. You have to duplicate. You have to show the row IDs everywhere. That can be a little bit messy for writes and slow writes and reads, right? That's why a lot of people use column-based in warehouses and stuff like that, and lakes, data lakes, where things are just almost static. They don't edit. They just do a lot of analytics on a single column. So that's powerful stuff, right? So let's go through these pros and cons in general. So for row-based, it's very optimal for read and writes, right? And then, well, I'm going to say read and write. I'm going to say transactions in general, online transactional processing, right? They are very great for this because they are very simple in their implementation. So, and if something simple, we can enhance it and make it more and more efficient as we go, right? That's why writes are fast. Reads are almost fast. It depends how your query looks like. We saw some examples, right? Online transaction protocols, processing, right? Transactions are great for row-based because you start a transaction, we know what rows, what blocks to touch. We can write the write ahead log efficiently because we know exactly what we're changing, right? Versus column, this little bit, the structure is all over the place, so we have to do a scatter shot Compression isn't really as effective though, because think about it, right? I'm not talking about the deduplication. That's something you can do in the index. I'm talking about just the idea of having the values uh, in the row. The row itself is almost distinct, right? It's almost like a hash because it consists of different fields, right? So you cannot really easily compress it, right? The compression algorithms is not gonna find a lot of tweaks to compress because the values are not consequent, right? Compared to the column oriented, where the consequent values are almost the same type and almost the same thing, right? So you're gonna get a lot of chances where of duplication. Like, so you get a lot of people named John, right? So Johns are gonna be squashed together. So compression is not as efficient with rows because you get all these different things that are next to each other and are completely different, so we can't compress as effectively. Aggregation, we saw how poorly the row based database did with the aggregation. I mean, we had to query the whole table, but we pulled lots of information that we didn't pick. So column oriented databases were more efficient when it comes to with aggregation because we fetch only what we need and we work on that. So if you started fetching information or data that are only what you need, then you're gonna start you be very, very efficient in your query and you'll only fetch the information that you need, right? So obviously you're gonna have a lot and you're gonna finish faster than row oriented databases. Efficient queries with multi-columns, right? So if you're picking multiple columns in a query or working with multiple columns, usually row oriented are better, right? And again, it depends. I'm talking only about the queries itself, right? So you can have a lot of columns if you want to, but if you're only working with a few of them, that's absolutely fine with column oriented databases. But if you're actually working and touching all these columns, that could be bad, right? With column oriented databases. With row, we saw it, right? A fetch on the row give us almost all the columns. Again, unless you have vertical partitioning. So with column based, writes are slower because we have to update all these beautiful structures. Every column has almost a structure on itself. Think of it this way: how is it stored? So I need to know where is it located and touch it every column, right? Like very similar to indexes if you think about it. They're perfect for online analytical processing. So if you're doing analysis, you're not touching, you're not writing, perfect column oriented databases. It compresses greatly because all similar sampling are together. So you can, the compression algorithms can do magic on these things and compress them. Amazing for aggregation. We saw beep brr, done. Right? That was amazing. I gotta admit. And finally, it's inefficient for queries with multiple columns. If you're asking for a lot of columns, don't do a column. Don't do column oriented. I know this is a little bit weird. You think that column oriented databases or column oriented data stores or columnar will be great if you're asking for a lot of columns. Nope, they are the worst with this stuff. I know, guys, Postgres, MySQL, other databases, most of them are row based storage. However, SAP HANA and others have Oracle, I believe. Most databases by default go with row-based storage. However, if you think about it, they have database storage engine, and we talked about database storage in my database course and in my YouTube channel as well. I talked about that. How a database engine, you can swizzle this database engine for a given table. So every table, you can pick a table and you store this table as column store, and you can pick another table and store it as row store. You can swizzle the database engine, right? Based on that, you can just change your database engine for every table based on the needs. If you have a table that only get queried, make it column, for example, right? If you're doing a lot of analytics on it, make it a column, right? If you're doing a lot of writes, probably you want to make it a row store, right? And think about all of this stuff. Like, you cannot, for example, join a row-based store table with a column-based table, right? That's just bad. I mean, some databases support this, but give them a break, guys. Give them a break, because that will be really disastrous. I can't even imagine what the database will do. It was gonna freak out, I guess. All right, guys, that's it for me today. What do you think about these two puppies? Let me know in the comment section below. I'm gonna see you in the next one. You guys stay awesome. Goodbye.
So I want to spend a few moments to talk about the differences between a primary key and a secondary key, or sometimes we call it a primary index or a secondary index. They are almost analogous. You might think you know the differences, but they are very subtle. And I want to talk about those two concepts in database system within the context of actual database platforms out there, Postgres, MySQL, Oracle, and how when we actually say a primary key, you get so much knowledge out of that word that will actually make you ask questions. It's not just that the fact that the primary key is unique, that is true, but it also gives you other kind of implicit information that will give you necessary understanding to optimize your queries, to know what you're doing when you're actually executing queries against a primary key or a secondary key. How about we jump into it? In order to explain what a primary key is, we really need to first explain the concept of the table spaces or the heap. When we're talking about a row store where you have rows in a table, we dedicate area in disk. We call it usually the heap in Postgres, or even in other databases as well, which is usually a slow access space, not much these days, but where all the data, expensive data, large data sits there, right? And the table is organized basically row by row. There is no order to a table. We don't enforce ordering by default. I'm assuming no primary keys or anything like that. You're just inserting data, and the rows come after each other. So if you insert a value of 7, it goes top. If you insert a value of 1, it goes to the bottom. And then if you insert another value of 2, it still goes to the bottom. It keeps appending. So there is no order that is maintained by default. Now, when we add the concept of a primary key, what we do to the table is we do something called clustering. And clustering is the idea of organizing the table around that key. So by default, we have to maintain order. And by default, the rows that you insert must fit that order. That means there is an additional cost associated with this ordering, right? The good thing we get because of this is like it's almost like an index in the table itself, if you think about it, but it's organized that way. That's why in Oracle they call it IoT or IoT, index organized table, right? Not to be confused with the Internet of Things, another IoT, right? And in Postgres or other database, they call it a clustered index, or when you say a primary key in general, that's what we understand. There is an index, and then in the heap, right? And the heap is organized around that index. So let's take an example. So let's say I insert a value of 1, right? And that value of 1 is my unique primary key. So there will be the value of 1 and all the rest of the row, like you have a first name and last name. It just goes there as well. It will be organized in that manner. So now if I insert the value of 8, right, it will go right under it, right? But if you now insert the value of 2, that value of 2 has to sit right after the value of 1, right? So you have to kind of push the value of 8 below so you can sneak in the value of 2, because they have to be clustered together. You have to maintain order, and as a result, if you obviously databases don't shift and left like this, right? They are smart. They have the page that they insert. They know, okay, value of 1 and value of 8, I'm not gonna put it in the same page. I'm gonna leave some space for the value of 2, 3, 4, 5, 6, and 7, because there are some values that need to be there. So the databases are smart. They're not, this is, I'm telling you about the naive implementation of things, right? And then when you do that, you'll get that extra cost. But the best thing that you can do with clustered indexes or primary keys is speed, because especially with range queries. So let's say if I asked you to give me all the values from 1 to 9, right? Especially range, that is almost like a one single IO. You go to the heap, which is in this case the index, and it's beautifully organized. So if you ask for these values, you get one IO, you get all these rows because they are nicely tucked together. However, in a configuration where you have a secondary index, that means the table is a jumbled mess, the value of 1 and then 7 and then 8 and then 703 and then the value of 1, then they are not organized, right? Again, I'm talking about a primary key that is random in nature here. Not all primary keys are random, right? That's why GWED is a bad idea to have as a primary key, especially as a primary key, right? Because the randomness nature of things, you will start jumping through the heap left and right. You will not benefit of the memory caching that the database is doing to insert these rows, which is something I talked about, some of the limitations of MySQL, which is, by the way, a primary key database. You have, by default, you have to have a primary key in MySQL, right? You get one for free, I believe, which is sequential, but you have to have one, and you have to have that means you have to have your table clustered in that way. Okay, Oracle give you the option to have the index organized table, but you don't have to, right? SQL Server, again, you have the option to have the index organized table, or they call it the clustered index in that case, a primary clustered index. You can have that option. So a clustered index that is sequential is not that bad, but you can get into other things that I don't want to spend more time in this video. We can leave it to another lecture. So that's a primary key. Let's move to the secondary key. The secondary key is having the table as a jumbled mess, but having an additional outside structure that is your key, that is your index, that is your B tree. It's not in the table. The table is a jumbled mess. So you have the value of 1, 7, and then 300, and then 7, and then 8, assuming there are no order, right? And now all the indexes, or the index that is pointing to your column, has no order in itself in the table, but it is ordered in another structure. So you're maintaining a separate structure for your indexes. Okay, that's called a secondary index. Now, if you want to search, you have to jump to this index first, do the search, collect the tuples or the pages that you want to query, because guess what? You're not gonna find everything in the index. Yes, you're gonna find the things that you're looking for, but not all the information is located in the index. You're gonna find the row IDs. You're gonna find that, oh, row number A is the value you're looking, and row number B and Z are the values that you're looking for. But you still have to go to the heap, to the table, to actually fetch the row itself, especially if you're doing select star on things. So you have to go do that jump. That's the disadvantage of secondary indexes. Postgres, all indexes are Postgres are secondary indexes. You don't have primary indexes in Postgres. Can you have one? I'm not sure. Can you create an index that is a clustered index? Maybe. I need to check. I think there's an option to cluster your table so that they are organized around that index. I prefer the Oracle term better than the index, better than the clustered index naming, or the primary key for that matter. Index organized table it's self-descriptive, and I love it, right? As opposed to the opposite, heap organized table, aka hot. Heap organized table is when you have the heap organize the tables. It's just random. There is no index that organizes the table, right? There's no primary key that fits that. And yeah, that's what I wanted to talk. I want to keep this lecture short and sweet. I hope you enjoyed this lecture. I guys, see you in the next one, and stay awesome. Enjoy the course.